Hi, my name's Colin Raffel. Thanks a lot for inviting me to give a talk at this very cool workshop. I'm an assistant professor at UNC Chapel Hill, and I do work on machine learning methods for learning from limited label data. And today I'm going to be talking about semi-supervised learning. And specifically, this is going to be kind of a speculative, loosey-goosey talk where I try to connect many modern approaches for semi-supervised learning back to the same principle, which is entropy minimization. So let's go ahead. So why am I talking about semi-supervised learning at a workshop about learning from limited label data? Well, it's because it's extremely effective as a method for learning a good model when you only have limited label data available, but you have lots of unlabeled data that's sampled from the same distribution as your label data. And to give you a sense for the kind of successes we've seen with semi-supervised learning over the past few years, I'm showing a bar chart here of what you might loosely consider the number of labels required to get 90% accuracy on the CIFAR10 dataset. So in 2013, when the max out paper came out, it was somewhat notable because it achieved 90% accuracy on CIFAR10 with standard fully supervised learning. So this was basically using 40,000 labeled examples-ish from CIFAR10 and attaining a 90% accuracy on the test set. And over time, after this paper came out, people improved on this little by little using the full label data set. But in around 2017, there was a nice semi-supervised learning method called virtual adversarial training that came out. And in that paper, it was sort of one of the first places people showed you could get 90% accuracy on CIFAR10 with only 4,000 labeled examples, which is decreased by a factor of 10, which is pretty good over the course of 4 years or so. And then a couple years later, some of my colleagues and I came up with a method called mix match. And in that paper, we ran an experiment on CIFAR10 with 500 labeled examples and got about 90% accuracy. And then a year later, we came out with a paper called fix match, which was sort of a simplified and improved version of mix match. And in that paper, we actually showed you could get 90% accuracy on CIFAR with only 40 labels per class. So we've now decreased the number of labels required by a factor of 1,000 compared to the fully supervised baseline. And that's quite exciting. And actually, there are other ways to improve this label efficiency. Semi-supervised learning is not the only approach. Notably, transfer learning can also dramatically improve label efficiency on CIFAR10, especially if you do something that everyone does, which is pre-train an ImageNet. But you use transfer learning in a different setting than you use semi-supervised learning. So transfer learning is useful when you have a related task with lots of data to learn from. And in semi-supervised learning, it's useful when you have a task with lots of unlabeled data available. So you have both labeled and unlabeled data from the same exact data distribution. So it's kind of different. In transfer learning, there's more of a shift there. So anyways, semi-supervised learning, very useful. So what I'm going to be talking about in this talk is kind of I'm going to propose to you a framework or an idea for why we've seen so much success in semi-supervised learning over the past few years. And it's a perspective I haven't seen people present before, so maybe you'll find it interesting. So to present this perspective, I will first review standard supervised learning. So in standard supervised learning, we sample data from the joint distribution of data and labels, P of X and Y, and we minimize the loss function showed on the screen here. So this is just your standard cross entropy loss. I'm being a little sloppy with my notation because this is a talk, but you can imagine that Y is a one-hot vector. And when we multiply the Y against the expression to the right of the Y, you can imagine we're doing a dot product, for example. That gives us the cross entropy loss. And it gives us a way of updating the parameters theta of our model, P theta Y given X, our model whose goal is to predict the class label Y given the input X. And so this is the standard loss function that everyone uses for supervised learning. And in semi-supervised learning, what we want is a loss function that doesn't require sampling from P of X, Y. We only can sample from P of X, right? Because an unlabeled data point is a sample from just the distribution P of X. We're not sampling from the joint distribution anymore. So we need to take an expectation over P of X. And what I'm showing on the screen here is a kind of meta loss function that many modern semi-supervised learning methods are minimizing for over unlabeled data. And there are various variations of this, and I'm oversimplifying things intentionally just to put everything kind of in the same framework. But you can see that this loss function looks a lot like the loss function we just saw. The main difference is that, as I mentioned, first of all, we're sampling from P of x, not P of xy. And second of all, instead of the y being the first term, our first term is P hat theta y given x. And I'm using P hat theta to basically denote some kind of modified version of our model. So it's not necessarily the model itself, P theta, it's P hat theta. So some kind of modified version. And usually we call this distribution produced by the modified version of our model something like a proxy label. That's what I called it in the title of this talk. Sometimes people call it a pseudo label or maybe a label guess. And the idea here is that we're using our model to produce a prediction about the label distribution. And we're kind of using that as our target, right? Because this term here is replacing the term y from the standard cross entropy loss. So we're, instead of using a true label y, we're using kind of a guess at the label or a proxy label that's being made up by our model. So to give you an example of a method that falls into this framework, showing self-training on the screen here. So in self-training, we essentially just take an unlabeled data point, we feed it into the model, get the prediction, and then we take an argmax to turn it into a hard label, like a hard class assignment. And so in this case, in terms of the terminology I just introduced, P hat theta y given x is just basically taking and adding an argmax around P theta. And that's what self-training does. And the nice thing about self-training is it's kind of intuitive. It's like, well, I don't have a label for this data point, so I'm just going to use the model to give me a label, and then I'll use that as the label and train the model to predict the label it predicted. It kind of seems a little weird because your model has to be good enough to predict good labels if you want it to get better. And so it's not necessarily clear why this will work, but it's very generic, right? As long as your model is outputting a distribution over labels, then you can use this. And most models can be thought of as predicting a distribution over labels, especially for classification problems. So we can apply it across domains, across problems, and kind of just, sometimes works. And sometimes it works really well. And there have actually been a bunch of recent papers that essentially use self-training to do really impressive things. So here I'm showing the diagram from the Noisy Student paper. And in the Noisy Student paper, fundamentally, they're using self-training. There's a bunch of extra steps involved. For example, there's a student model and a teacher model, and the teacher model is the one that generates the pseudo labels. And there's also a bunch of regularization that gets applied, but fundamentally, they're doing a form of self-training. And actually, this idea of self-training is pretty old. You can trace it back pretty far. Here's one paper from 1965 that introduces something that's effectively self-training, where basically they say, instead of using labels for data points, we're going to use the model's prediction for as labels. And so this is an old idea. It gets reinvented all the time under lots of different names, but it's nice because it's somewhat intuitive, and like I said, sometimes it works pretty well. So I said sometimes it works. Now the question that's probably on all of your minds is, well, when does it work and when doesn't it work? So that's what I'll try to answer now. So I've put the sort of standard self-training equation up on the screen again here, and I'm going to modify this equation a little bit. I'm going to drop the argmax. Okay, so the argmax was the thing that took the model's prediction and turned it into a hard label assignment. And if I drop the argmax, then P hat theta just becomes P theta, right? There, we're basically just using the model itself to generate the distribution to train against without a hard label assignment. And if I plug that in to my sort of standard cross entropy style equation that I introduced earlier on, we get something that looks like this. Now, some of you are probably stroking your chin and going, that looks like the entropy. That's exactly what it is. It's the entropy of the model's predicted class distribution. And so if the point being here is if we just set P hat theta to P theta, so if we just feed the model's output back in as the target to predict, well, now we're just minimizing entropy. So our loss function just becomes entropy, and we're minimizing entropy. And indeed, this is a semi-supervised learning method called entropy minimization. And you can kind of think of entropy minimization as, well, I'm going to feed an unlabeled example into my model. My model's going to come up with a prediction, and I'm going to try to minimize the entropy of the model's prediction, which is to say, I'm going to try to make the model more certain. I'm going to try to make as many of the class probabilities 0 and one of them 1. That's my goal. That's what entropy minimization wants to do. And this still doesn't really explain why this works. It's not totally clear why we would want to minimize the entropy on unlabeled data points, but that's what an entropy minimization does. And just to connect this back to self-training, if you plot this loss function for a model that has a single output, so a binary classification problem where there's a single logit on the model, and you plot the loss with respect to the value of that logit, then these are the two loss functions. One of them is entropy minimization in blue, and the other is self-training in red. And you can see they look very, very similar. And you can imagine that the model probably has somewhat similar behavior, whether you use entropy minimization as your loss function or self-training. So again, the only difference here is that the self-training has an argmax. It has this sort of discretization step, and that's why we get this sort of sharp loss function that's shown in red here. But overall, sort of the shape, and you can imagine the effect of these two loss functions is quite similar. And actually, sometimes people say things even more sloppy, like self-training and entropy minimization are equivalent. They're not, but they are quite similar in their behavior. And entropy minimization, I would maybe trace it back to this paper. If you have an earlier reference, feel free to send it to me. But this was an interesting paper from NeurIPS in 1991, where they essentially show that if you have unlabeled data, something reasonable to try to do would be to try to maximize the mutual information between the input of the model and the output of the model. And you can do this on any data point, right? You don't need a label to do this. You just need to say, I want the model's output to reflect as much information as possible about the input. And if you just write down the definition of mutual information, plug things in, simplify, you get this expression on the bottom here, which has two terms. One term is just entropy minimization. The other term is an interesting term that basically says, when I average across my entire data set, I want the model to have predicted every class with equal probability. So basically, if I feed in the full unlabeled data set, or marginalize over P of X, and I average out over all of the class predictions, I want it to be a uniform distribution over classes. And that's interesting. You could imagine it being useful in a class balance problem. And actually, people have used kind of similar things as auxiliary losses, but really we care about entropy minimization here. So let's focus on the entropy minimization term. So now I will try to give you an intuitive explanation as to why entropy minimization might be a useful thing to do for semi-supervised learning. Because again, it's not totally obvious that just making the model more confident on unlabeled data is actually useful. So here on the screen, I've showed a very simple two-dimensional two-class classification problem. We have black dots and white dots, and the goal is to train a model to separate the black dots from the white dots. And with only this data, it's kind of unclear what a good decision boundary should be. You can imagine various kind of straight lines that could run through this plot and separate the black and white points. But there's lots of such lines, and it's not clear which one is the best, and if maybe there's some underlying structure in this data set that we want to capture. And so you could imagine if we're given a bunch of unlabeled data shown in with little gray dots here, we might have a better sense of what a good decision boundary is. I mean, visually, it's kind of clear there are two moons here. There's these two kind of semicircles of data. And you might imagine, based on where the black dots and the white dots show up, that the top moon is one class and the bottom moon is another class. So if you just drew a straight line through this plot, you would cut right through the two clusters of data, these two moons. So that might not actually be a very good decision boundary for your classifier. You probably want a decision boundary that cuts through the low density regions in the input space, right? You want the model to not cut through the clusters, because if you cut through a cluster, it means that stuff that you think is probably the same label is going to flip labels when it flips the decision boundary. And so now if we imagine one of these bad classifiers, one that goes through the two clusters, like this straight line here, you can see this classifier actually classifies the labeled data perfectly, but it goes through these clusters, and we don't want it to do that. And so I'm plotting from red to blue here, kind of the class, you can imagine like the class probability output by this model. So this model is smoothly interpolating between class 0 in red, the black dot class, and class 1, sorry, class 0 is in blue and class 1 is in red. And so there's the smooth transition from class 0 to class 1 as you cross the decision boundary. And now if you look at the entropy of the model's prediction for unlabeled data, and you look near the decision boundary, like I'm showing here with this little histogram and the arrow, that point is going to be classified as class 0 and class 1 with roughly equal probability, right? So when you're right on the decision boundary, you're going to be assigning a 50-50 probability to the two classes. And that distribution is very high entropy. The uniform distribution has the highest possible entropy. So for an entropy minimization objective, this would be very bad. We would not want this at all. So if we imagine that we've applied entropy minimization, we might get something like this. So this is a decision boundary that is avoiding the unlabeled data. And you can see that now all of the data tends to have, or it's more likely for a given data point to have a lower entropy prediction, right? Because it falls further away from the decision boundary. And because the decision boundary is smooth, the farther away you are from the decision boundary, the lower entropy your predictions are. So as long as the classifier is smooth, entropy minimization incentivizes the model to pass through low density regions of space. And that's kind of falls into the assumption that we made earlier about what a good decision boundary would be. It would be one that goes through the low density regions of space. And so hopefully on this toy example, you can see why this would be useful. But notably, it completely relies on the fact that this model smoothly interpolates between class 0 and class 1, right? It's and in fact, if you have a model that can make an arbitrarily sharp decision boundary, this is what you might get, right? So this actually is a very good solution for entropy minimization, right? Because basically every point in this plot has a very low entropy prediction, right? Because either the model's predicting class 0 or class 1. There is no smooth transition between the two classes. It just flips from one to the other. So entropy minimization is perfectly happy here. So what this suggests is that maybe in order to get entropy minimization and therefore self-training, because again, self-training has a very similar loss function to entropy minimization, maybe we need a model that is forced to have a smooth decision boundary. And up until this point, some of you might have had this plot in mind because most of you probably train neural networks all day. And when you train a neural network, we're quite used to the fact that the model can make really sharp decision boundaries. We can, especially on the training data, it's very easy over the course of training, assuming that the training set is small enough, to get the model to predict the class label basically exactly. That means that our loss has gone to 0. If the loss is 0, it means that the model is predicting all of the training labels exactly. And those are all very low entropy predictions. And so we all train neural networks, so we might expect the model to come up with this bad solution to the entropy minimization objective. But self-training is useful. People use self-training all the time. Entropy minimization is useful. People use it all the time. So what are they doing? Well, it turns out that what they're doing is basically regularizing the model. So if we regularize the model, then the model is kind of forced to have a smoother decision boundary. And how exactly to regularize the model? Well, that's kind of something that we figure out empirically, but you can see, for example, in the Noisy Student paper, indeed, they do apply a significant amount of regularization when using self-training. And just to give another random example, this was a paper talking about how to improve pseudo-labeling, which is equivalent to self-training. And their main claim in the paper is that if you use mix-up, which is a very powerful regularizer, you can start to get self-training to work. So again, in order to get self-training to work, we need to use some kind of regularization. And hopefully you can see intuitively why that's true. So now I'll talk about kind of one other very effective form of semi-supervised learning that people use these days. It's called consistency regularization, and mix match and fix match, for example, on that plot that I showed at the beginning of the talk, both use consistency regularization. And what consistency regularization does is it takes an unlabeled data point and it augments it, and we train the model to predict the output for the unaugmented image when the model is fed the augmented image. And again, that's kind of the most common form. There are many other implementation details here. For example, people often apply a stop gradient operation between the loss and the model for the unaugmented image. But let's ignore that for now, again, because we're being a little bit sloppy to make everything look like it's the same. And you can see on the bottom here how I would map consistency regularization into this framework, this like cross entropy against a modified version of the model. And in this case, the modified version of the model is just the model taking in an augmented image as input. So we just augment an image, feed it into the model, and that's our target. And again, we end up with a very, very similar loss function that we've been discussing so far. Now, in order to kind of connect this all back to entropy minimization, I'm going to do something that people often do when they talk about neural networks, where they kind of decompose a neural network into two parts. One is where the model extracts some learned features, and the second is where the model takes those features as input and into a simple classifier and performs its classification. And the nice thing about training neural networks with gradient descent is that we can train these two pieces jointly, but people often conceptually decouple these two pieces, the feature learning and the classification steps. And so it turns out that if you train a model with consistency regularization, specifically I'm showing a model here that was trained using fix match, the fix match algorithm, and you train it until it works well, in this case, this was 40 labels total, so 4 labels per class. And you feed in augmented versions of various images, and you compare the distance between the learned representation for the clean image and the augmented image. Then this is the distribution of those distances. I'm plotting cosine distance here. And you can see that for the most part, the cosine distance is very close to 0. And what that basically means is that the learned representation doesn't really change when you augment the input image. So to some extent, the representation learning chunk of the model is invariant to augmentations. It outputs the same representation when you augment the input. And that's good, right? It means that it's invariant to the stuff that we think it should be invariant to, because usually data augmentation applies transformations that the model should be invariant to. So that's good, and that's why we call it consistency regularization. We want it to be consistent when we feed in augmented versions of the image. And what this also means is that if I have a feature extraction pipeline and it outputs some feature for a given input, and I feed that feature into a classifier, and then I augment the original image, get a new representation, and feed that into the classifier, the classifier essentially now has the same input, right? Because if the feature representation doesn't change when the input changes, I'm basically feeding the same thing into the classifier in both cases. And what do we get when we apply the cross entropy between a model, a classifier, that's fed the same input? We get the entropy, right? So if we're minimizing that loss, we're doing entropy minimization. So as long as the model, as long as the representation learning part of the model is invariant to augmentation, then the consistency regularization loss is essentially doing entropy minimization on the classifier. And now there is one thing that some of you might be thinking. You might be thinking, well, the image shouldn't change classes when we apply the augmentation. And when you do representation learning, you're also trying to learn a representation that's invariant to class, right? Basically, I want a good way to learn this model would be that the representation learning part outputs the same representation for all inputs of a given class. That makes the classifier's job very easy. So you might be thinking, well, maybe the model has just figured out how to do that. And so it's not actually the consistency regularization and entropy minimization that's working here. It's something else. And kind of to address this point, I'm plotting here, if you take different images of the same class and show a histogram of their cosine distances, you can see it's much less close to 0. It's much less concentrated around 0. And what this means is that indeed, they tend to be pretty close to each other. The different images in the same class tend to have representations that are pretty close to each other before they're fed into the classifier. But you don't get this really intense peak distribution around 0. So it really is the case that the model is much more invariant to augmentation than it is to class. So hopefully this convinces you that entropy minimization is lurking behind the scenes, not only obviously for self-training, but also for things like consistency regularization too. And hopefully this has also given you a sense of why entropy minimization is even a good idea in the first place. So that's all I will say. Thank you for watching my talk. And if you have any questions or want to follow up on anything, my email's on the screen here. Thanks.